This video is going to be discussing the concept of polarity in molecules. And polarity becomes incredibly important when we're looking at molecules and life and how they interact with each other. Without polarity, we would not have life. So before we start talking about polarity, we need to revisit the idea of electronegativity. And just a reminder, electronegativity is an atom's ability to gain an electron. So for example, fluorine, which is in the corner of the right side of the periodic table, it has 9 valence electrons. And because of those 9 valence electrons, that's reflective of having 9 protons. That's the important piece. Those 9 protons are going to be able to pull those electrons closer than, let's say, for example, lithium that only has 3 protons. Remember, each electron feels the full force of all of the protons in the nucleus. Okay, so lithium only has, each electron of lithium only has 3 protons pulling it towards the center, where fluorine has 9. So we notice that in this reddish area, red-orange, that's where you have atoms with the greatest electronegativity. That means that they have a high ability to gain electrons. This becomes important when we actually discuss polarity, because polarity is all about the tug and pull of electrons. So we're going to kind of narrate through this comic strip because it does a wonderful job of describing polarity. And it uses a penguin and an ice cream cone and an ice bear, or a polar bear. So I'm going to read through this comic strip and then embellish the information, hoping that that's going to clarify some things. So you don't have to go to the ends of the earth to find polar molecules. They're all over the place. A polar molecule is just a molecule with a difference in electrical charge between 2 ends. And so what that means is polarity in molecules is caused by difference in electronegativity between atoms. So if you take a look at this hydrogen and chlorine that is attracted to each other, you notice that we have a little cloud where you have a plus end and a minus end, plus end at the hydrogen and a minus end at the chlorine. And this is about that tug and pull tug and push of electrons. So again, just a reminder, electronegativity is the ability of an atom to attract bonding electrons towards itself. So let's use the analogy of the penguin with an ice cream cone and the polar bear. You notice the penguin is hydrogen and the chlorine is and the polar bear is chlorine. So we have a pair of bonded electrons. Those are the 2 scoops of ice cream. And the chlorine wants those those electrons, and hydrogen does also. And so it's a tug of war. Who's going to clearly win this tug of war? It's going to be the polar bear, because chlorine is more electronegative than hydrogen. So the bonded pair of the electrons in HCl spends more time near the chlorine. In other words, because the polar bear is stronger, he's going to have the electrons closer to it than the hydrogen is, because it can pull it closer. And for that reason, you have this region, chlorine, being negative. Remember, electrons are negative. And because electrons are more likely going to hang around the stronger of the 2 atoms, that this end of chlorine is negative. And as a result, because they're no longer the electrons so close to hydrogen, that becomes positive. So just a reminder that in the periodic table, something we've talked about, this region is the area that has the most electronegativity. And noble gases are often not assigned electronegativity because, remember, they have 8 valence electrons and they rarely bond with other atoms. Okay, so when two atoms of different electronegativity values bond, the bonding electrons spend more time around the more electronegative atom, creating what we call a partial negative charge on that atom. And the other atom has a partial positive charge. So here is just reintroducing that idea that chlorine is more electronegative. The polar bear is more likely to get that ice cream closer to it and keep it around that. In other words, chlorine is more likely to keep the electrons closer to it. And electrons being negative means that that area is slightly more negative than the hydrogen, the penguin there, because those electrons are not often or as much around the hydrogen. Now, in the case of when you have two of the same elements or atoms bonding together, when atoms with equal electronegativity values bond, they form something called non-polar bonds. Okay, and that means that the tug and pull of each of those, or in other words, the electron attracting strength of each atom is the same. And just to remind you, up here, it's not the same. So for that reason, we call these polar bonds. However, if the electronegativity of two bonded atoms are different, then their bonds will be polarized, just a little, or maybe a lot. Depends on the actual element. Because elements have such varying electronegativities and can bond in many different combinations, and we've seen that when we've done our dot diagrams or our molecular structure, there's really a continuum of polarity in bonding. We can break the continuum down in 3 categories. So we have the nonpolar bonds, covalent bonds. That's when you have two of the same element bonding together. So the clearest examples of nonpolar bonds are those between identical atoms such as H2, N2, O2, Cl2. And that's because they've got two of the same atoms with the same electronegativity competing against each other. Bonds between atoms with nearly the same electronegativity value, such as carbon and hydrogen, can also be considered nonpolar. Now, polar covalent bonds. In a polar covalent bonds, two atoms are shared bonding pairs of electrons somewhat unequally. The electrons are more attracted to one atom than the other, and examples include bonds between carbon and oxygen atoms or between hydrogen and fluorine atoms. And then lastly, the thing that we've been talking about a lot last semester and the beginning of this semester are ionic bonds, and these are much stronger bonds. A large difference in electronegativity results in a winner-take-all situation of ionic bonding. The more electronegative an atom takes the bonding electrons and becomes a negative ion, while the other atoms becomes a positive ion. And those opposites charges on the ions attract each other. And this is our classic example, what we've been doing all along, where sodium loses the electron to chlorine. Okay, they have such huge differences in electronegativity. The chlorine takes the electrons away. When we're talking with molecules, remember, their electronegativity isn't quite as different, and so they instead share the electrons. So bonds between atoms create dipoles. The word dipole can refer to the polarity of an individual polar bond between atoms and the net polarity of individual polar molecules that have several polar covalent bonds within it, and the polar molecule itself. So you will notice that here we have an arrow. We literally have a vector to show that. So let's go ahead and take a look at some examples, and then I'll work through some examples. Let's start with the nitrogen on the left. So in this case, it is a non-polar molecule because remember that tug and pull is equal. They equally share the electrons, so there's not one region that's more positive or negative. However, for the HCl, which is here on the right, remember this is where you have a stronger electronegative atom, and it's pulling the electrons towards it. So what we want to do is we want to show a vector where we're showing where the pull is happening. We start with a positive symbol at the end. And if you look just above the HCl, you'll see this vector. The positive symbol shows where your positive region is, and the arrow shows which direction the electrons are being pulled. And so in this case, the electrons are being pulled to the chlorine, and that's why you have the arrow pointing to the chlorine. So this is an example of two atoms where you can see its polarity. Now in some cases, you've got three atoms, and they're doing a tug and pull equally. So CO2 has two dipoles, but the CO2 molecule itself is not a dipole. So it has polar bonds, but those polar bonds balance each other out because they are equal and opposite tugs and pulls, and that makes them nonpolar. Now this is different to water. Water has this sort of bent shape. We'll be discussing that a little bit closer. And you notice that water has a polar bond. The hydrogen is more positive than the oxygen. And so the electrons are moving towards the oxygen. However, these two vectors are not canceling out. And so for that reason, you have a polar molecule. That means in this case here, that the oxygen is still pulling those electrons closer to it than the hydrogens, okay? So, having said that, let's kind of end it with a couple of thought questions. I'll reduce the size. So, if a penguin represented a hydrogen atom and the polar bear represented a chlorine atom, what does the ice cream represent in the drawing? And what do you think the picture is trying to illustrate? What type of bond? And lastly, would hydrogen chloride be attracted to a charged wand that has a charge? What would you think your answer to be? So, returning back to our presentation here, let's go through some of these examples, and I'd like you to include those in your notes. So, for the first example, we have chlorine, two chlorines. So, the easiest way to determine if they are polar or nonpolar is by drawing your molecular structure. Okay, and this is where those lone pairs are really going to come into play. Now, from what we had seen in our comic strip, we know that when we have two atoms that are the same, that they have an equal push and pull. So this is considered non-polar. All right, and the way that you can determine that is, are the electrons, these lone pairs, equally distributed on both sides? And the answer is yes. All right, so we've got electrons surrounding this entire molecule, and they are equally distributed. Now let's make things a little bit more challenging. Here we have carbon. There we go. And we have the hydrogens coming out. Now, when I look at these, for our purposes, we're going to say that carbon, let's just take a look at carbon and hydrogen by itself, all right? Carbon and hydrogen are not the same atom, and so for that reason, they don't have the same electronegativity. And if you look at your electronegativity chart, you will recognize that carbon is more electronegative. For that reason, this is more electronegative. which means the electrons are going to hang around carbon more likely than they are hydrogen, because carbon is stronger. We're going to show a dipole by showing this is where we're going to have the plus sign. Remember, plus equals less electrons around it. Okay? So we had said that carbon was stronger, so it's going to be pulling those electrons towards it, which means hydrogen has electrons, less electron spending around it. And so we draw a dipole where it points to where the electrons are spending most of their time. So in that case, you've got a dipole right here. We've got a dipole right here. We've got a dipole right here. And we've got a dipole right here. Remember, each one of these bonds will have its own dipole. Now we need to step back and take a look at this picture and see, do our dipoles actually, are they equal and opposite each other? And if they are, they cancel out. So this dipole right over here this dipole is equal and opposite to this dipole. Okay, so for that reason, these cancel out. Now let's take a look at the other two dipoles. This dipole is pointing to the left, and this dipole is pointing to the right. They are equal and opposite, so these cancel out. And so for this reason, this is considered a non-polar molecule with 4 polar bonds. Okay, so we know that each of those, the carbon and hydrogen, have a polar bond where one region is more positive and one negative, but when they all come together, they cancel each other out. All right, let's try this one here. This one is arsenic. Arsenic has 5 valence electrons. This one you might find to be a little bit easier, and I'll tell you why. So in this case, you can step back, even though you have definitely some polarity upon the bonds. This right here, this lone pair trumps all. A lone pair will always have high electron concentration because they're by themselves. They don't need to share any electrons. There is a huge cloud of electrons here. This alone is going to show that this side is negative and this side is positive, just because of that lone pair. I don't even have to do dipoles, because as soon as I see a lone pair, I know this is a polar molecule. So that's why I've always been focusing on, do not forget your lone pairs, because if you see a molecule with lone pairs, you know it is polar, no question about it, okay? So that would be an example. All right, let's try this one. This one is going to be an interesting one. Okay, I'm not going to forget my lone pairs. There we are. So for this one here, I have clearly 2 types of bonds. I have a chlorine and an iodine bond, and I have a chlorine and a fluorine bond. Now when I look at my periodic table, remember the top right-hand corner has the highest electronegativity. That means that for carbon and iodine, you definitely have iodine being more electronegative. So you're going to see that there is a dipole going to iodine. So carbon, remember, is further left. Iodine is further right. That means iodine is more electronegative. The dipole, the electrons are going to be pulled to the iodine. Now, looking at carbon and fluorine and comparing that to the iodine, you'll notice that fluorine is not only to the left, but it's also to the top left, which means that fluorine is even stronger than iodine in pulling its electrons towards it. So I'm going to show a much longer vector. And the reason is, based on the periodic table, fluorine is a highly electronegative atom, and so that means it's going to have most of its electrons from the carbon being pulled towards it. So I need to show that in a dipole. And this is where those dipoles come into being quite handy. So remember, fluorine was showing a dipole of great strength. We're making that really long. Whereas carbon and iodine, the iodine is sharing its is pulling its electrons towards it, but not as strongly as would carbon and fluorine. So these two will cancel out, but the fluorine to the iodine that are north and south, those don't cancel out, because even though they're opposite directions, they are not equal. That makes this region be negative and that region be positive. The last one we're going to be doing is this molecule. And the nice thing about this molecule is all I need to do is look for the lone pairs. I see that I have lone pairs. I automatically know that this region is negative and that region is positive. This is a polar molecule. I'm going to have you try it now on your own.